How's it going, Diego? Can you even see over there? Can you even see over there? Yeah. You're okay?
I'd rather not turn around.
Y'all should slide the table down so you're not. Just push it down a few feet. That way you're not so close. How are y'all doing? Seems kind of thinned out a little bit here today.
Do I hear attendance quiz?
Maybe we'll do that. All right, so from last class, we had two main results, all right, from last class, which are this one and this one, which allows us to take the derivative of any logarithmic function and any exponential function. Now, the formulas that I have up here are similar to what you would find on your formula sheet, the ones that are starred here. And there's also these two are on your formula sheet also. Now, the difference between the two that are not starred and the two that are is what? What is the difference? I mean, this is the derivative of any logarithmic function. This one is the derivative of the very special natural log function, which is when the base is e. All right, so this is a special case, this is a special case. But these two that are starred are the more general formulas. So what you can see in this first formula is that this formula incorporates the chain rule into it. So if you want to take the log of, the derivative of log base a of u, the answer is 1 over u. So you just rewrite whatever's in here, you just rewrite it down here. Then you multiply by natural log of a. A is the base of the logarithmic function. And then you multiply that times the derivative of u. That's the part right there, the u prime. That's the chain rule. That's you going from the outside in and taking derivative of what's in here. All right, and then you could slide that u prime up top, and then it gives you this formula right there. Okay? Now, if the base is e, it's the special natural log, and this part right here becomes a 1, and that's why it does not appear in the formula. So you just get 1 over u times u prime, or if you'd like, you can just write it as u prime over u. Now, with the exponentials, same thing, taking derivative of a number raised to some function. The answer is just itself times natural log of a, which is natural log of that number. And then chain rule says now take derivative of what's up here, which is the u prime. And then the special case of e to the u, it's the one where it's its only derivative. But you also have to account for the chain rule. So we're going to do some examples of this right now, and then we're going to move on to a special kind of well, a new technique for taking derivatives. Yes?
U stands for a constant, right?
Okay, so the question is u stands for a constant. In this particular case, u is some function. It's actually not a constant, because then derivative of this would be 0, right? Okay, so let me give you some examples, and you'll see how this. Let me leave those up there for now. How about I give you an example of each one of these right next to it? All right, so I'll just make like a table out of this, so you can see a specific example of each one of these. Okay, so like here's an example of this. Let's say we have log base 3 of x squared plus 4x. All right, and we want to take the derivative. Understand this notation? Okay. So according to the formula, this should just be 1 over what? So this is the u, right? This part right here is the u in the formula. So it's 1 over x squared plus 4x. Now I need that in parentheses because it has two terms. That's 1 over u. Then natural log of a. So natural log of 3 down here, then times u prime. So the derivative of this, which would be 2x plus 4. Yeah, plus 4. Is that all right? The only other thing you really could do here is you could take this 2x plus 4 and put it on top. Just slide it up on top. That's your derivative. So does that formula make sense? Okay. Now let's take a look at the next one. Let's do like natural log. Let's do natural log of, did I do this last time? Did I do sine x last time? Natural log of sine x? No? I did? Well, let's just do it anyway. There, natural log of sine x. So I want to take the derivative of this. So according to the formula, u is sine x, right?
Yes.
So this is going to be 1 over u, so 1 over sine x, times the derivative of sine x, which is cosine x. And that is cosine x over sine x, which is cotangent x. Yeah, I think I did do that last time. Okay? Let's take a look at this one. What if we have 7 raised to the, let's keep it simple here again, x cubed plus x. And I want to take the derivative of this. So according to the formula, all you're going to do is write the entire function down again, right? Don't change anything. It's the exact same thing. So 7 raised to the x cubed plus x. But then multiply that times what? Natural log of 7. And remember, natural log of 7 is just a number, okay? That's just some, so this is like this is a constant. And then I still have more, right? Then the chain rule says now I need to take derivative of what was up there. So the derivative of that up there is what? 3x squared plus 1. And I need that in parentheses because it has 2 terms. So this is the derivative of this. Y'all okay with that? All right, and then e, let's do one of these. How about e to the tangent x? If I want to take derivative of that. So according to the formula, the derivative of e raised to anything is itself. So e to the tangent x. But then multiply that times what? The derivative of tangent of x, which is secant squared x. So you have to go back and remember when we were doing derivatives of trig functions, derivative of tangent was secant squared. And that's it. That makes sense? All right, so I would say that these 4 examples are basic examples of derivatives of exponentials and logs. Because in these derivatives, notice that everything that I put in here, like this right here, we call that the argument of the function. This argument, the derivative was very clean, wasn't it? This argument, the derivative was very clean, cosine. This one, the derivative was very clean. And this one, of course, very clean. So let's try and crank it up a little bit and make the argument perhaps a little more complicated, or let's throw the log into a product rule or something like that. That way we start to see some different variations. But this is the basic idea of how you do derivatives of logs and exponentials. All right, let's try something here. So we're going to do a bunch of examples now. How about, let's say y is equal to the square root of x plus 2 natural log x. And we want to find y prime. So we do have a logarithmic function in here, right? This right here? That looks like 21, but it's natural log, okay? Now 2 times natural log of x. So there's my logarithmic function, but it's inside of a bunch of other stuff, right? So if we're looking at this kind of from the perspective of all the different rules we've learned, which are power rule, product rule, quotient rule, chain rule, and now these other rules, we have to incorporate all of those together now. So what do you see happening here? Chain rule, right? You have like a composition of functions. You've got all this happening in here, which is just a sum, but the outer function is the root. So we start out with trying to take derivative of the root of something. And what is the derivative of the root of anything? 1 over 2 roots of that stuff in there, right? X plus 2 natural log x. So that takes care of the outer function, square root part. Now multiply that, because chain rule says multiply now. Multiply that times the derivative of this stuff right there. That is a sum, so I can do them individually. The derivative of x is 1. So I need this in parentheses because I'm going to have more than one term. So 1 plus, now the 2 in front is just going to come along for the ride, right? Because it's attached to the natural log by multiplication, so it's just going to come here like this, 2 times, and now derivative of natural log of x is just 1 over x. Close the parentheses. So if I wanted to, maybe I could write it like this, 1 plus 2 over x over 2 square roots of x plus 2 ln x. That's it. Is that okay? Okay, let's try something else. Let's just tweak this problem a little bit, okay? I'm just going to tweak it. I'm going to redo this in here, and instead of doing x plus 2 natural log of x, I'm going to go 2x natural log x. So I've removed that plus between them, and I've turned it into a multiplication in there. Y'all see the difference? Let's see how that impacts our derivative. So we still have a chain rule here, don't we? Still have chain rule. So we're going to still start off with the derivative of the root of something. So that should give us 1 over 2 roots of that something. So 2x natural log x. Chain rule says multiply now by the inside, the derivative of the inside. And so when we look at this now, 2x times natural log of x, kind of gave it away there, but times means product, right? Product means product rule. So we have multiplication I just grabbed this out of the office. Okay. Yeah, they're trying to, heads up over there, I'm probably gonna hit you. All right, so here's multiplication. It's weird. So we got a little multiplication right there. So if you need to, you could just do this on the side. If you were asked to take the derivative of that, right, you would do your little product rule on that. So you do derivative of this times this plus derivative of this times this, right? So derivative of this would be 2 times natural log of x plus, what's derivative of natural log of x? 1 over x times 2x. And that's kind of interesting because this x and this x cancel, don't they? So you just get 2 natural log of x plus 2. Right, that's that little product rule. And that needs to be tacked on to the end of this. So in parentheses, I'm going to put 2 natural log x plus 2. I could even go a little further if I wanted to. I could move this up top, right? And I also noticed that in the numerator, they both had 2's, didn't they? And I had a 2 on the bottom. So couldn't I factor out a 2 up here and then cancel these? So maybe like natural log x plus 1 over root 2x natural log x. That would be a cleaned up version. I kind of skimmed through my video solutions today for 3.3, and it's a pretty long video, but I do almost all the problems. And there's, you know, if you go through those, you'll see every problem has got some product rules and maybe some quotient rule in there. They get pretty involved. I did have some students ask me about 3.1 and 3.2. I believe there is a homework assignment on the list, is that correct? But there's no video for it. And that's because 3.1 and 3.2 is really kind of an optional thing. That's a review from college algebra. So if you feel like you need to go back and do that, go ahead. But you know, I don't have any solutions out there for you, just so you know. But 3.3, it's all there. Okay, how do you feel about this? That's all right? Okay, so far it's okay? All right, good. All right, let's change it up a little bit more.
Could you have gotten rid of the square root before you took the derivative and then?
So the question is, could I have gotten rid of the square root before I took the derivative? How would I get rid of the square root?
By bringing it to like a 1/2 one.
Oh, make it a 1/2? Okay, yes, but then you would still have to do the power rule. Like you would have to bring the 1/2 out and then all that and subtract 1. You know what I'm saying?
Yeah, I did that for like the first one.
Yeah, you can do that. We get the same answers. They just look different because one of us is using radicals, the other one's using rational exponents. I recommend that if you see a square root, stick to the 1/2 root of whatever's there, because that's kind of should be like an automatic thing.
Okay.
Yeah? Okay. All right, let's try something else. How about x to the 4th plus 4 to the x over log base 2 of x plus x. Yeah, let's just do that. So what do you see here? Everyone see a quotient rule? Okay, so we need to do a quotient rule here. And the quotient rule says I'm going to take the derivative. I'm going to go slow here because we haven't done a quotient rule in quite some time. I'm going to take the derivative of the top. So I'm going to take the top right here. I'm going to take its derivative. Then I'm going to multiply that times the bottom. And then minus the derivative of the bottom times the top. Got it? All over bottom squared. Right? That's the setup of the quotient rule. So really all I need to do now is take two derivatives, this one, and I'll be done. I'm not going to really clean it up. This is going to be pretty ugly. So this is going to be equal to, let's see, what is the derivative of this? So derivative of x to the 4th is 4x cubed plus, because I have addition here, and now what's derivative of 4 to the x? 4 to the x times natural log 4. So that is kind of forcing us to understand the difference between the derivative of a power function versus an exponential function. Those are the two derivatives we get. Questions there? Okay, times log base 2 of x plus x. Okay, minus now another derivative. I need to take derivative of log base 2 of x. 1 over x times ln2, And that's it for that, because we have inside the argument of this log function is just x. So when you do the chain rule, the derivative of the inside is just 1. So you don't have anything else that pops out here. Okay, what else am I needing here? Plus 1. That's the derivative. That's plus derivative of x is 1. And I need that in parentheses. And then times x plus 4 to the x. And then all over the bottom squared. Okay, so that would be the derivative right there. There's not a whole lot we could do that would clean this up and make things like cancel and go away and get nicer. It's ugly.
There's a way to make these problems easier, right?
There is another, yes. Well, slightly easier. This one could go a little easier. Are you talking about like logarithmic?
Yeah.
Yeah, we're going to do that today. All right, let me make sure that I have a decent variety of problem. Okay, this one's, yeah, I think this one's a good one to look at. Something like this. My goodness. Okay, look at this one. Natural log of the square root of x to the 4th plus x over 3 plus x squared. Before I begin this problem, well, let's talk about it. If you were to go and attack this right now, you would see what, chain? Chain rule? What's the outer function?
Square root.
Natural log. Okay? What would be the next function inside that? Square root. And then inside that, you would have your quotient, right? So you would have like chain, and then at the end you would have some quotient rule to do. And we could do that, all right? We could do that. However, I want us to go back and I want us to remember a couple of things about logs. And I put these properties up last class, but I'll stress them again. That if you have log, and I don't remember how the formula was in the notes, but I'll use n and m. If you have division inside of a log, right, that can be turned into 2 logs with subtraction. All right, that was one property. We have another one for multiplication, right? If it's multiplication, it becomes addition, but we don't need that here. And then we have this other very important property that natural log of x to the n is equal to n x natural log x. In other words, if the argument of the log function is being raised to a power, that you can pull the power out front, right? Okay. So before I start this problem, I just want to rewrite something here. Yeah, I'm going to change that square root to the 1/2 power. Do you all agree with that? That's the same thing. And then if I use this property says natural log of something raised to a power, the power can come out front, can't it?
Yes.
So I'm not doing any derivatives yet. I'm just rewriting this algebraically. So this becomes 1/2, comes out in front of the natural log, and then I still have in there x to the 4th plus x over 3 plus x squared, right? And then I can use this property that allows me to turn division into 2 different logs. Now, what about that 1/2 that's out front? It's going to go to both. So this is going to split into 2 logs, but the 1/2 is going to go to both of them. So I'm going to have 1/2 natural log of what? X to the 4th plus x, and then minus 1/2 again, natural log of 3 plus x squared. So again, no calculus at this point. This is all just algebraic manipulation. In college algebra, we would have called this expanding the expression. taking this single log and expanding it out into two different logs. Y'all remember doing that in college algebra? Something like this? This is kind of why, all right, you did it, is so that when we get here, we can take a derivative now. See, it's going to be much easier to do a derivative of this because now I have two separate logs. And notice that we don't have any sort of like complicated root. Like here we had a natural log, then we had a root, and then inside that a quotient rule. Notice we're not going to have any more quotient rule, right? We don't even have a root anymore, right? The root's not even in here. We do have a little bit of chain rule. We'll have to do natural log of this and natural log of that. That'll be a little chain rule, but it's not as complicated as the original expression would have been. Yes? Okay, so let's go for this now. The derivative of this. So we have two separate terms, so I'm going to do them separately. Derivative of this one, the 1/2 is going to come for the ride. And then what is the derivative of natural log of something? 1 over it, right? 1 over that something times, now chain rule, the derivative of what's in here. So 4x cubed plus 1. Is everyone clear on the derivative of this being that right there? Okay, and I'm done with this, right? There's nothing else? Move on, minus 1/2. And then derivative of this piece right here, which is 1 over 3 plus x squared times 2x, the derivative of that. Now, had you not used those properties, you'd probably still be doing that problem. I mean, it's messy. Let me see. Can I maybe clean this up just a little bit? How about we do this? 4x cubed plus 1 over 2x to the 4th plus 2x. So all I did here was took this, put it up here, and I distributed the 2 through to both of these terms. Is that fair? Then I have over here, see, I get those 2's cancel. This x can just jump on top of that there. So we just have minus x over 3 plus x squared. And that's pretty clean, wouldn't you agree? That's pretty clean. I just want to show you, just so you can see it, if we had not done the algebra, I just want to show you what the appropriate derivative would have looked like. Okay, just what it would have looked like if I did not do all that, those properties. I would have had that y prime would have been, well, derivative of natural log of something is 1 over that something right, times the derivative of the something, which is a root, right? And the derivative of a root is 1 over 2 times that root times, now the derivative of what's inside, which would have been quotient rule. So it would have been 4x cubed plus 1 times 3 plus x squared, then 2x, and then x to the 4th plus x, and then all over the denominator squared. That's what the derivative would have looked like had we done just chain rule right off the bat. Now, I mean, things do happen. I mean, like this root and this root go together and the root goes away, right? So imagine this and this coming together and the root going away. Can you imagine that happening? So it'd look like this. Yes? And then 1 over a fraction reciprocates, so this would flip and basically be this on top of this. The 2 would still be down there. And then you'd have to go through this and clean it up. Eventually, you could maybe get it to look like that. But they would have both been correct answers, just one version would have looked different than the other. And the book does talk about that within the section. They do talk about how you can get a correct answer and they just look completely different from one another. And it's always a good challenge to see if you can algebraically make your answers match up. But okay. How about this one? y is equal to x to the fourth times 4 to the x squared plus 1. That just looks weird. That's why I wanted to use that or do this one. Can you see what's happening here? Be a product rule. The product is occurring right here. So what would the derivative of this be? So we're doing derivative of the first one, which is 4x to the third times 4 raised to the x squared plus 1, right? So that's the beginning of the product rule. That's f prime g. Now plus g prime. So now the derivative of 4 raised to the x squared plus 1. So it's itself 4 raised to the x squared plus 1 times natural log of 4 times 2x. That is just the derivative of 4 raised to the x squared plus 1. Finish off the product rule, though, times x to the fourth. I will do some cleaning here. 4x cubed times 4x squared to the x squared plus 1. And then plus, what do we have here? These I can put together? That's 2x to the fifth, isn't it? Okay, so I'm going to write 2x to the fifth times natural log 4 times 4 to the x squared plus 1. That looks a little better, I guess. Questions there?
You could combine bases on first.
With the 4?
Yeah.
I could do that. I could do that, but I'm going to factor it. This right here is fine the way it is, but I'm going to factor. I do have a greatest common factor in both of these. Now, this factoring step is not necessary, but remember that we were eventually getting to the point where we wanted to set the derivative equal to 0 to try and figure out where our tangent line might be horizontal. Now, that's what the next chapter is about, but I've told you that we need to be able to set these equal to 0 at some point. So if I needed to set this equal to 0, I could factor out, I could do a 4 to the x squared plus 1, but then I could also pull out an x to the third power and a 2. So I could pull a 2 out, an x to the third, and I could pull out a 4 to the x squared plus 1. And what that would leave me with in here is what? 2? That's all I'd be left with here, right? Over here? So plus x squared natural log 4. So if I had to set these things equal to 0, I could now, because I've factored it. All right. How about this one? E to the e to the x. Yeah, so remember the derivative of e to the u is e to the u times u prime, right? That's our formula from earlier. So for us, this right here is like the u, isn't it? We have e to the u. And u in this case is e to the x. All right, so the derivative of this should be e to the u. So just to repeat itself, right? E to the x times now the derivative of the u, the derivative of what's up there. And what's the derivative of e to the x? E to the x. So it's e to the x times e to the x. That's the derivative. All right. Why, I don't know why I put x, or 1, x. There. So that is properties of exponents. Remember that if you have x to the n times x to the m, it's x to the n plus m. So if you have the same base, different exponents, you have multiplication, then you just add the exponents. So I have same base as e. Here's two different exponents. There's multiplication between them. I just add the exponents together. So that's the same answer. Okay? You all okay with that? All right. How about secant to the fourth of natural log of ax plus b? Yeah, there's chain rule here. Now we cannot use the properties of logs that I had shown earlier because the log is inside of stuff. It's not by itself. So, I mean, it's not outside, so we can't use those convenient properties to kind of expand this out. So we're just going to have to go with the chain rule. What is the outer function here? Is it the fourth power or the secant? Which happens last? Fourth power. So remember, this expression is the same as that expression. Okay? That fourth power is the last thing that happens. So do you want me to leave it like that or put it back the way it was? Just leave it? Okay. So if I want to take the derivative here, chain rule, I better give myself some room. Chain rule says I start with the 4, right? 4, and then it's all of this, right? I'm not going to touch it. By the way, x is the variable here. A and b are constants. Unless someone tells you differently, always assume x is your variable, and any other letters in there are going to be constants. The book does mention that somewhere in the beginning. So am I done? What, I'm missing something here. Cubed. Okay, so the 4 came out, the power comes down by 1. So all I've done right now is I've taken the derivative of that part. What's the next layer inside the chain rule here? Secant. And remember, the derivative of secant x is secant x times tangent x. Right? Secant x times tangent x. So I'm going to have to put here times secant, but not x. Secant of what? All that stuff. So it's secant of natural log of ax plus b times tangent of natural log of ax plus b. That is pretty nasty looking, isn't it? But that's the way it is, all right? This is like your secant x tangent x, except that it's not x. It's all that stuff. Feel good? Okay, we've dealt with the secant part. And now we're down to the natural log part. What's the derivative of natural log of something? 1 over it, so times 1 over ax plus b times now the derivative of what was inside the natural log, just a. So I'm actually just going to slap the a on top there. Okay, so there should be an a out here, but I just slid it up on top. That's your derivative. Yeah? All right. You need to just do the homework for this section because there's so many different variations of the problems in here that I need to do at least 50 of them to give you the same variety that the book does. Let's do another one before I show you this new technique. Okay, how about this one? Y equals e to the x sine 2x. Find the equation of tangent line at the point 0, 1. So I claim that this point lives on this graph, and that if you were to graph it, you're going to have a tangent line there, and I want the equation of that tangent line. So we need its derivative, right, so that we can get the slope. So the derivative of this, well, we have e raised to something, right? So derivative of e raised to something is itself, e to the x sine 2x, then times what? Derivative of what was up there. And that's going to require what? Product rule. There's a product right there. So, and a little bit of chain, yes. So product rule says derivative of the first one times second plus derivative of the second one times the first. So derivative of the first one is 1 times sine 2x plus, now derivative of sine of 2x is cosine 2x times 2. Don't miss the 2. Where's that 2 coming from? Derivative of sine of something is cosine of it, but then you have to go inside and take derivative of 2x, which is 2. So that 2 is important. And then, what? I'm still not done. Times x. That's my derivative. Okay? So what is the slope of the tangent line then? Remember, I'm going to be using this formula here to come up with the equation of the tangent line. I already know y1 is 1, and I already know that x1 is 0. All I need to know is what's this m, right? And the m comes from this. But how? I have to plug in 0, right? The x is 0. I need to plug 0 into this and see what I get. And it's actually kind of boring. I get 0, don't I?
Yep.
Well, that sucks.
Oh, yeah.
I get 0 because sine of 0, right, is 0. And then 2 times 0, that's 0. So this is 0 plus 0, which is, this whole thing is 0. And this doesn't matter because that's 0. So we get 0 when we plug in. I was hoping it wouldn't look like that, or it wouldn't work out like that, but oh well. Okay, so at x equals 0, we get that y prime is 0. Y'all okay with that without me doing the work? Okay? So now if I come back over here and I replace this question mark with 0, then all you get is y minus 1 equals 0, right? Which means y equals 1, which is a horizontal line, like this. It's 1 unit up. So let's do it. I'm curious to see what that graph looks like. Where the heck is? We've used Desmos a few times, right? Okay, so I'm going to graph, what was it, e exponential raised to the x times sine of 2x. And then I'm going to graph 1. Y equals 1. There it is. Okay. Can you see that? It's kind of a mess up here, but where is it? There it is. Okay. That's a pretty cool looking graph. So the red one is the original function, the red one. And if we go to the point 0, 1, which is right here, and we look at the graph and we try to find the equation of tangent line, it's that blue line, and that's y equals 1. Yeah? It would have been more interesting to find the slope of a tangent line maybe like, I don't know, somewhere around here, but that would have been a harder point for me to come up with. I just, in my head real quick, just plugged 0 in and got 1. So, all right. All right, let's take a look at, we're gonna change gears, switch gears here a little bit. Let's take a look at a rather ugly function, all right? All right. Let's take a look at this. Y equals x plus 1 to the 7th times 2x minus 3 to the 8th times x minus 4 to the 10th over x plus 3 to the 4th times 4x minus 1 to the 6th. That's a 6. And then x plus 2 to the 12th. And we want to find y prime. I think so. I think if we're talking about the same thing, yes. So this is not a very nice looking problem, because just think about what would be required here. All right? You have a quotient rule, don't you? So you'd have to do derivative of the top times the bottom minus derivative of the bottom times the top, all over this whole bottom squared. But when you take the derivative of the top, look at that. I mean, it's not just a single product rule, it's actually multiple product rule, which is more challenging. And then when you do that, you're going to have chain rules in each of those. Very, very ugly looking thing, isn't it? No one would want to do that. So we have a special type of differentiation when certain functions look a certain way. And it's called logarithmic differentiation. All right, logarithmic differentiation. Now this is in your notes, so let me bring up your notes real quick, and that way you can see what I'm referring to here. And we'll come back to this problem. Okay, logarithmic differentiation. Okay, we can use the properties of logs to aid us, okay, to help us in finding derivatives. This method is called logarithmic differentiation. Here are the steps. Here's what you're going to do. You're going to take the natural log on both sides of the equation y equals f of x. You're going to differentiate implicitly with respect to x, and then you're going to solve for y prime. Now, those are the steps, but let me just show you that in action. We start off by having an equation, y equals our function of x, right? And then I'm going to take the natural log on both sides. See, it's called logarithmic differentiation, but there are no logarithms here, right? Yet. We have to introduce the log. So what we're doing is we're relying on a property from logs from college algebra that said this. If y equals x, then natural log of y equals natural log of x. This is a property from college algebra with natural logs. And it has to do with the fact that the natural log function is what we call one-to-one and onto. One-to-one and onto. It's a bijection. So basically, and that's usually kind of a little bit further out than what a lot of students at this point understand. But it just means that when you map something through the natural log function, natural log of x, that when you map it over, every point here, okay, this x here goes to this y. Then let's say there's another x, so I'll call that x1, this one y1, this one x2, this one y2, that every point over here, every number here goes to exactly one place here, and everything over here goes back to exactly one place here. So you have a function that is one-to-one, one input to one output, and onto means everything over here gets hit by something. Again, it's beyond what we really need to talk about, but the way you can look at this property is that if you have an equation, you can always take natural log of both sides. We're not technically taking natural log of both sides. That's what I'm going to say we're doing, but we're actually just using this property, that applying the log does not change the equality. Can you live with that? Okay, so at this point, using the one-to-one onto nature of natural log, I can say that the natural log of y must be equal to the natural log of all of this, right? Now, I don't feel like rewriting it, so I'm just going to stick it back up here. I have the advantage that I can do that. Okay. All right. Yes? So I'm supposed to, according to the steps I said, I take natural log on both sides, right? And then I'm supposed to take the derivative implicitly with respect to x. Implicit differentiation, not your straight differentiation. This is that special differentiation that we use with related rates. So we're going to be taking the derivative of the left side and the right side with respect to x. But the fact that I have a log here now allows me to use the properties of logs to simplify it first. Don't we have log of something divided by something? Mm-hmm. And when you have division, can't you turn that into subtraction? Yes? Okay, so watch. I'm not going to do any derivatives yet. Just check this out. This is going to become very nice in just a second. This is going to turn into natural log of x plus 1 to the 7th times 2x minus 3 to the 8th times x minus 4 to the 10th minus a different natural log, and this one is going to be x plus 3 to the 4th, 4x minus 1 to the 6th, and then x plus 2 to the 12th. Y'all see what I did there? That's just using a property of logs. And then we have multiplications inside these logs, don't we? And wherever you have multiplications, you can split those into additions. So this log with these three factors can become three new logs, can't it? So I'm going to continue. Natural log of y equals natural log of x plus 1 to the 7th plus new natural log 2x minus 3 to the 8th plus another natural log x minus 4 to the 10th. Any questions on what I did here? This turned into this. Now we have to be real careful here because we have a subtraction, don't we? And that subtraction has to impact everything over here, and I'm about to split this into three new logs also. And each one of them is going to be plus, 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 yes? Yes. But I'm going to pass the negative through. Okay, so it's going to be minus, minus, minus. Natural log of x plus 3 to the 4th minus natural log of 4x minus 1 to the 6th minus natural log of x plus 2 to the 12th. We're almost there. There's one more property that we can use right now. What property? All the powers can come down. The 12 can come, the 6 can come, the 4 can come, the 10 can come, the 8 can come, the 7 can come. Right? So we have natural log of y equals 7 natural log of x plus 1 plus 8 natural log of 2x minus 3 plus 10 natural log of x minus 4 minus 4 natural log of x plus 3 minus 6 natural log of 4x minus 1 minus 12 natural log of x plus 2. Bam. And this is something that I'm willing to take the derivative of, because each one of these by themselves is not that difficult, right? The 7 will come for the ride, Derivative of natural log of this is just 1 over this, right? Times the derivative of what's inside. Pretty clean. Same thing here, same thing here, same thing here, same thing here, right? So I think it's time for a derivative. Do you see why this is pretty useful? This logarithmic differentiation? Okay, so here we go. Derivative time. So when I do the derivative now, I'm differentiating with respect to x. So here it comes. And you have to be really careful on the left side of the equation, because you have to take derivative of the left side also. So what is a derivative of natural log of y? I'm going to, yes, it's 1 over y, right? Derivative of natural log of anything is 1 over it, right? 1 over y, and then times the derivative of what's here, right? Which is dy dx. I'm just going to write that as y prime. Is that fair? Dy dx? That's the derivative of the left side. We're done on the left. On the right side, 7 times derivative of that. We said the derivative of this is going to be what? 1 over x plus 1. That's it, right? So it's just going to be 7 over x plus 1. Okay, be a little careful here. The 8's going to come for the ride. Derivative of natural log of 2x minus 3. So the 8, yeah, I'll do the 8 in a second. Hold on. So derivative of just this, just the natural log part, is 1 over this, right?
Yeah.
Times the derivative of what's in here. 2. So it's really 2 over this, isn't it? 2 over this, but then times the 8. So 16 over 2x minus 3. So ignore the 10 for now. Derivative of natural log of this is 1 over that, right? Times the derivative of what's inside. So just 1. So what's that going to be? 10 over x minus 4. Are y'all following this? Are y'all catching on to how these derivatives are so much cleaner and easier than the other stuff we would have had to have done? Let's see, what would the next one be? Minus 4 over x plus 3? Or x plus 3, yeah. Next one? Minus 24 over x, 4x minus 1. And the last one, minus 12 over x plus 2. Yes?
Yes.
That's a pretty clean looking derivative right now, isn't it? But it's not the derivative. This is not the derivative. This is actually equal to the derivative times 1 over y. We don't want this. So what we're going to do now is we're going to multiply both sides by y. Okay? So if I multiply this side by y, it goes away, right? If I take this whole side and multiply it by y, then I have what y prime is, right? But what is y? Y is the original function. Yes? Y is the original function? So I'm going to write my answer now. It's going to look horrible. But the derivative, how we got it, is not that bad. I think maybe, am I saying too much there? It's not that bad? Okay, so look. All right, I forgot what the problem was. What was the original y equals? It was, hold on, I might be able to. Okay, hold on. X plus 1 to the 7th. Hold on, let me do this myself. Let me see if I can figure this out.